The recent report of the first-ever X-ray detection of the interstellar object 3I/Atlas marks a major milestone in observational astronomy and significantly expands our understanding of how objects from beyond the solar system interact with the space environment around the Sun. This groundbreaking observation was made using the Soft X-ray Imaging Telescope STEND onboard the X-ray Imaging and Spectroscopy missions RISM, a collaborative space science mission led by the Japanese Aerospace Exploration Agency JAXA. Until now, interstellar objects had never been detected emitting X-rays, making this discovery both unprecedented and scientifically important. The observation not only confirms that interstellar bodies can generate detectable X-ray emissions, but also demonstrates the advanced capabilities of modern X-ray observatories in studying faint and distant phenomena. XRISM carries two main scientific instruments, STEND and RESOLVE, each designed for different but complementary purposes. STEND consists of an X-ray telescope that focuses incoming X-rays and a highly sensitive X-ray CCD camera that records the resulting signals. One of STEND's key advantages is its exceptionally wide field of view, measuring 38.5 arc minutes on each side, which allows astronomers to capture extended structures such as diffuse gas clouds or cometary comets. The second instrument, RESOLVE, provides high-resolution X-ray spectroscopy, enabling scientists to analyze the energy distribution of X-rays and identify the chemical and physical processes responsible for their emission. Together, these instruments make XRISM particularly well suited for studying faint, extended X-ray sources like 3I/Atlas. The X-ray image obtained by STEND spans a projected square region approximately 3 million kilometers on each side, centered on 3I/Atlas. Within this vast area, astronomers detected a faint but clear emission glow extending up to 400,000 kilometers from the object's nucleus. This glow represents the X-ray signature of the interaction between the interstellar object's coma and the solar wind, a stream of charged particles continuously flowing outward from the Sun. Prior to this observation, 3I/Atlas had been detected across a wide range of the electromagnetic spectrum, including ultraviolet, visible, infrared, submillimeter, and radio wavelengths. However, X-rays had remained elusive, largely because of the faintness of such emissions and the technical challenges involved in detecting them. The discovery of X-ray emission from comets within our own solar system provides important context for understanding this result. X-rays from comets were first discovered in 1996 with the observation of Comet Hyakutake, a surprising finding at the time because comets are relatively cold objects and were not expected to emit high-energy radiation. Subsequent studies revealed that cometary X-rays are produced primarily through a process known as charge exchange, in which highly charged ions from the solar wind collide with neutral atoms and molecules in the comet's coma. During these collisions, electrons are transferred to the solar wind ions, releasing energy in the form of X-ray photons. This mechanism has since been confirmed in many solar system comets, establishing cometary X-ray emission as a well-understood phenomenon. What makes the detection of X-rays from 3I/Atlas particularly remarkable is that this object originated outside the solar system. Interstellar objects are thought to be remnants of planet formation processes around other stars, ejected into interstellar space by gravitational interactions. When such objects pass through the solar system, they offer a rare opportunity to study material formed under different stellar and planetary conditions. The fact that 3I/Atlas shows X-ray emissions similar to that of solar system comets suggests that at least some physical processes governing cometary activity may be universal, operating in much the same way regardless of an object's origin. The characteristics of 3I/Atlas made it an especially promising target for X-ray observations. It is believed to have a relatively large mass and an extended coma, providing a substantial volume of neutral gas that can interact with the solar wind. A larger and denser coma increases the likelihood of charge exchange interactions, thereby enhancing the resulting X-ray emission. These properties distinguish 3I/Atlas from earlier interstellar visitors, which were either too small, too inactive, or observed under less favorable conditions to produce detectable X-rays. The timing and execution of the XRISM observation were critical to its success. XRISM conducted a target of opportunity observation, a special type of observation reserved for transient or time-sensitive events that cannot be scheduled far in advance. This observation took place about 1 month after 3I/Atlas passed its brightest phase of perihelion on October 29, 2025. During perihelion, the object was hidden behind the Sun from the perspective of Earth-based and many space-based observatories, making direct observation impossible. Additionally, XRISM itself has operational constraints that limit observations to regions of the sky that are at least 60 degrees away from the Sun, in order to protect its sensitive instruments and maintain stable thermal conditions. Once the geometry of the object's position relative to the Sun allowed safe observation, XRISM began monitoring 3I/Atlas from 2320 Universal Time coordinated on November 26 to 2038 Universal Time coordinated on November 28, 2025. Over this period, the total exposure time amounted to approximately 17 hours, providing sufficient sensitivity to detect the faint X-ray emission. During the observation, 3I/Atlas drifted slowly across the constellation Virgo, reflecting its motion relative to both Earth and the background stars. To ensure that the object remained near the center of Sten's field of view, the satellite's pointing altitude was adjusted 14 times, roughly once every 3 hours. This careful tracking was essential for maximizing the quality of the data and minimizing systematic uncertainties. The resulting X-ray detection represents a significant technological and scientific achievement. From a technological standpoint, it demonstrates the precision pointing and stability of the XRISM spacecraft, as well as the sensitivity of the STEND instrument to extremely faint and diffuse X-ray sources. From a scientific perspective, it opens a new observational window on interstellar objects, showing that X-ray astronomy can play a role alongside optical, infrared, and radio observations in characterizing these rare visitors. The implications of this discovery extend beyond the study of a single object. X-ray observations can provide unique information about the interaction between interstellar material and the solar wind, offering insights into the composition and structure of the coma, as well as the properties of the surrounding plasma environment. By comparing the X-ray characteristics of interstellar objects with those of solar system comets, astronomers can investigate similarities and differences in their physical and chemical properties. Such comparisons may help determine whether interstellar comets are fundamentally similar to those formed around the Sun, or whether they represent a broader diversity of icy bodies shaped by different stellar environments. Moreover, this detection suggests that future interstellar objects passing through the solar system could be viable targets for X-ray observatories, particularly if they exhibit significant activity. As survey capabilities improve and more interstellar objects are discovered, coordinated multi-wavelength campaigns, including X-ray observations, may become increasingly common. These efforts could greatly enhance our understanding of the building blocks of planetary systems throughout the galaxy. In summary, the first X-ray detection of the interstellar object 3I/Atlas by XRISM's STEND instrument represents a landmark achievement in astrophysics. It confirms that interstellar objects can produce detectable X-ray emission through interactions with the solar wind, extending a phenomenon previously known only for solar system comets to objects of extrasolar origin. The observation highlights the capabilities of modern X-ray missions, underscores the importance of flexible target of opportunity observations, and opens new avenues for studying the physical nature of material formed around other stars. As more interstellar objects are discovered in the future, this pioneering result will serve as a foundation for further exploration and deeper insight into the diversity and universality of cometary processes across the galaxy.